right, okay, so we are back. 1 minute felt quite fast. All right, great. So now we've talked about simply supported beams. Now let's talk about the cantilever, which I explained earlier on. Okay, so we can see these here are cantilevered structures. Let's look at their represented elements over here in the analysis. So let's come over here and set this. Let's go over here and turn this off for now. We're going to be looking at this cantilever. So before I go ahead and look at the results, let's understand how it works, right? Just like I explained earlier on, you can see that this time around it has the support here, but this other end here is free. Okay, likewise as well, this one has a support and this other end is free. Now the difference is that this one here is fixed, and the difference between this one here is that it is pinned. Okay, now let's go ahead and look at this. I'm going to isolate the elements so we can see them. Let's look at the results. I'm going to go over here and turn on the bending diagram. Alright, great. And we can see here that this is how the structure is behaving under the bending. Now the scale here is actually quite large. Let me go ahead and reduce it. Okay, good. So we can see here that this is the bending nature of the beam. Alright. Now for the fixed here, you will see that anytime it is fixed, it has high generated loading at this point over here, and it goes all the way to this point at the free end as 0. Okay, at 0. But we see here that when it is pinned to free here, moment is generated here, moment is generated here as well. Now for designers, we prefer to use the fixed to free when we are designing cantilevered structure. In fact, for most structures, we always decide to use fixed supports, right, as opposed to what we actually do when we are in school. Now if we leave it like this, what it means is that there's going to be quite a lot of load at this point here, meaning that the end of this beam here, let me just show you, the end of this beam here is going to require quite a lot of reinforcement, or it will require the beam to be very, very deep, and that is not an economic approach when we are designing beams. So that's the reason why we prefer to assume that the other end is fixed when we are designing. Okay, all right, great. So this is basically how a cantilevered beam works. All right, okay, now let's look at something else. We're still on beams, and now let's talk about continuous beams over here. Let me show you the respective elements. So these here are continuous beams, and look at it here, it's actually broken down 1, 2, 3, right? Likewise as well, 1, 2, 3. Okay, now the only difference is that at the supports here, this is fixed, at this point is fixed, or let me show you here. So you can see here that at this point here it is fixed, this point here is fixed, this point here it is fixed, this point here is fixed. Or in the other case, we have it to be pinned all through. Now let's go ahead and look at the results, how it will actually look like. I'm going to come over here, back to moments, turn on the MY, and then I'm going to click on apply. Okay, it's just going to wait for that to load. All right, good. Should probably isolate this to make it easier to view. Let me go ahead and isolate this structure. Right. All right, great. So I'm going to increase the scale so we can actually see the diagrams a lot better. Okay. Okay, good. I'm going to increase it a little bit more. It's just a little bit more. I want to show you something very vital as we are looking at the beam. It's 300 scale, feels quite. Alright, let's say 530. Let's see how that works. Alright. Okay, so as I increase this scale, like I said before, if you have any questions, feel free to let me know. Okay, great. Alright, good. So now we can see here that there's a difference between how these two structures are actually showing their representative analysis models. So we can see in the first place here, just because we have a fixed support, there's moment generated here. But once it gets to in between two beams, so a beam before the support, another beam here before the support, we can see that moment is generated here, But aside from moments being generated, we have here restricting moments because of this restricting rotation because of the support. So what it does is that it generates moments here, and then it either increases or reduces depending on how the other span is loaded. All right, so for instance here we can see here that it goes like this all the way from, let me be sure everybody's following. All right, so it goes like this all the way from the bottom, it goes all the way to this point over here, and then you can see that the moment it drops, right? Now this is a clear indication that this particular beam here is not as loaded as this particular one here. All right, and I'll show you just to be sure that we are on the same track. So we're back here in the physical. I'm going to go over here and then turn on the structural loads. Let me see if I can show you this. Right, okay, good. So we can see here that we have here the loads. So we can see here that the magnitude of the load on this beam here is not as high as the one here. And we can see here that it's not as high as the one on the other end of the beam. Now, all these loads actually affect how the structure is going to behave and the analysis that it is going to show as well. All right, great. So just thought I'd show that as well, just to be sure. And that's what causes this. So you can see here that because the loading on this beam here is smaller, it reduces, and then you can see bending is now generated towards the center of the beam, and then it goes all the way to this point here. And because the loading on this other end of the beam here is larger than this, you can see it will increase, and then the same thing happens all the way here. All right, great. So that's how to actually understand, especially by looking at these results. Okay, it's vital. But when we look at pinned all through, we can see that because there is rotation allowed to happen here, we don't have that that drop or increase in moments over here. It either increases and then just continues over here. And you can see that over here, this particular beam here has a very small moment at the center. Now, we always, as engineers or designers, structural engineers, we tend to prefer the fixed method all through because it shows a more accurate depiction of how the structure will behave under the loading. Most of the time, actually, how it was done in the past through manual processes, that we actually compare the three, and whichever one is the highest, we actually pick. Because that can actually be very time consuming, because you can see in the fixed case here, we can see here that this is 21.14, but in this case here, this is 43.59. Right, so yeah, that's actually a high difference. But through testing and models, we determine that the fixed method is always going to give us the more accurate model, or there's actually what we call a superimposition method, where it actually superimposes all the cases together and then determines what is good. So the software can go ahead, for instance, and say, okay, this and this is to join this together. So at this point here, we have 43.59 as the one we use to design this span. Over here, we decide to use 13.64. Over here, we decide to use 35.79. So it's, as designers, we prefer to use the higher value for the worst case scenario. All right, good. So yeah, that's just quite a lot on beams. We're going to be going over to the next type of member, which is columns, if I remember correctly. All right, great. So let's go back here to the full diagram over here. We're going to, just like I mentioned earlier, we're going to be walking all the way to this point where we have the more complex structures, but the understanding of it from the simplest terms is what will enable us to get it better. All right, so at this point here, I want to ask if you have any questions, just let me know. I'll be glad to address them as well. Likewise as well, if you do have questions or questions come up after the meeting, feel free to send them to the general channel on our Slack platform, and then I'll be there to guide and direct you as well. Also, you can also send the personal or direct message through the direct messages medium on Slack. All right, great. So let's see. All right, so if you have questions, just let me know. We'll just continue in the absence of questions for now. Now let's go and talk about columns. So for here, scrolling here, we can see that this here are columns as opposed to beams. Now columns are quite different in the sense that here columns are generally used to transfer loads that are coming from the floor to the foundation. So for instance here, let's look at this particular structure. Okay, you can see here that this is the slab, and the loads of the slabs are sent to the beams, and then the beams send the loads to the columns, which are actually sent to the ground. Okay, so over here, we ideally look at columns as what we call compression members, meaning that they are loaded just like this. So they are meant to be compressed. So this end here, the top here, is going to be taking the loads all the way down. So it's compressing it from the top to the bottom over here. And we can see how columns behave under different materials and section sizes. So in the first situation here, we can see that we have columns subjected to axial forces. Now these are only columns that are loaded at the top only, and I'll show you an example. So if I go over here and turn on the model, we can see that we have a point load just directly on top of the column over here, right? And you can see here that this column here is a C20 and this one is a C40. Okay, now basically the material does not actually determine how much the column can take, but more or less the section size. All right, so more or less, because it's a compression member, it's going to require more. It's going to require you to increase in section size rather than increase the material. Although sometimes the higher material can actually take more loads, but most of the time it is always ideal to increase the section. Like I mentioned earlier on, that increasing the material or choosing a higher material may be more costly. All right, so I'm seeing a question from Victor. Okay, so I'll read it out now. He said, I would like to understand the significance of the bending moment values. Some are negative and some are positive. When designing, which of these values are most preferable? Okay, this is actually a very, very good question. And we'll actually, once we got to the design aspects, we're going to cover it. But let me go ahead and do a brief explanation on that. All right, if that's fine. So let's look at this coming here. Let's come back here to the analysis. I'll use the continuous beam because I believe that here would be a good way to explain it. Alright, good. So we can see that at the spans here, let me go ahead and increase this. Increase the scale. Alright, so we see here that at the spans here, we have what we call positive moments, right? So if there are positive moments, you can see that the diagram as well is going to the bottom. When you have positive moments, especially in beams, it means that when we are going to be putting our reinforcement, it's going to be at the bottom, right? So across this whole span, probably from here to here, the reinforcement position will be at the bottom of the beam. But when we get to supports, and supports are normally between two beams, you notice that what designers will do is that they will put the reinforcement position at the top. All right, so that reinforcement is meant to resist that moment that is generated at that particular point. All right, so I don't really have a graphic representation here, but probably as we go on I will show you. But I hope that I was able to answer the question, Victor. Just let me know if that was able to answer the question. Okay. All right, good. So let's go back here to the models over here. All right, good. So just like I explained over here, so these two columns are loaded. All right, and then based on how they are loaded, it will determine whether it's going to require a larger section or not. All right, now it's going to be a different case when the column is just loaded from the top, right? Most of the time as well, columns can also be loaded from the sides. So an example, for instance, can be something like this, right? You can see, apart from the column being loaded from the top here, it also has a UDL coming at the side, right? And this bending is only in one direction. Now, what you would actually notice is that most of the time when designers are designing columns, and you see that they have loading coming in this direction, right? If the column cannot take it, right, or rather the capacity of the column is not sufficient, meaning that this, let's say this column here, for instance, is a 300 by 300, by the way. If it cannot take it, what we'll do is that we increase the depth of the column in that direction. So you can see that the depth has increased. So that means that now it's be able to resist the load in this direction. Now it would be a mistake if the column orientation were like this, right? Because we have more of the loading coming from here. So that means the larger depth should be in this direction, just like this. Now this is just bending, or rather the being loaded in one direction. We also have as well bending in, rather this should be two direction. Let me just go ahead and change this. That should be two directions. All right. Okay. Alright, so bending in two directions. So apart from it being loaded here, it's also loaded at this side. So let's assume this smaller column can't take it. What it means is that it would have to be like this as well, right? So the same principle applies. Wherever it is loaded the most should actually have the larger depth, just like how it is displayed over here. Now let's go ahead and look at some of the analysis values for the columns. I'm going to come back here and let's go and focus on the columns. I'm going to reset this. Alright, so we have here the first set. I'm just going to select some of this. Oops, missed one. Alright, now I have all of them. Okay. If I go, for instance, here and check here the let's check the moments. Now for columns, you can check it in both directions, right? So I'm going to go ahead and check it in one direction, for instance. Okay, no, sorry, this direction rather. um, Let me increase the scale. Hold on, just let me quickly. Alright, so it seems the Alright, so that's one of the beautiful things about structures. So it seems the load was actually so small that the loading is actually quite negligible on the. Oh, sorry about that. Yeah. So the loading is so small, it is very negligible on the column. So we can actually see values here. Let me just go ahead and see if I can show you something more precise, because in this application, it may not really give you a better representation of those values. So I'll bring in my analysis software, and we have, if I remember correctly, we have those same columns here. Let's look at some of the results. Okay, so yeah, the loads are so small that it doesn't actually put in so much value. So probably before the presentation, I should actually have gone ahead and put in something quite magnificent. Okay, so yeah, the values aren't too much for it to handle. Okay, I think we have something at my. So let me see if I can show you this. All right, yeah. Okay, so we can see this here. Let me increase the scale. All right, so we can see here that this is the moments being generated in just one direction, which is in this direction over here, right? So remember that the column was loaded like this, right? So if you want to check it in the other direction, we can check. Let's check X direction, for instance. If I click on X, so the X is so small that it doesn't really show anything over here. All right. So the same thing also applies to columns, and I just wanted to illustrate that just to be sure. Now let's go and look at something else. All right, good. So yeah, let's go and look at something else. So we have here members subject to torsion. Members subject to torsion. Now torsion is also something we have to look at when we are designing structures. So for instance, let's go ahead and show how this structure has been loaded. If I click on this, go ahead and turn on this loading icon, you can see that apart from the beam being loaded like this here, we have loading going in this direction on the beam, and we have loading going in this direction on the column. All right, let's go ahead and look at how those values affect the analysis. If I come back here, let me go and just isolate that particular member. All Alright, let's just go and isolate it. Alright, so I'm loading up the analysis on it. Okay, so at this point here, just want to ask if you have any questions, feel free to let me know. Also, I do recommend as well, try to take down notes, because how we understand the basis of structural design determines how we end up designing the structure, right? So it calls for less rework, especially when we are working on a live project. Okay. So now I'm going to go ahead and turn on the bending on the structure. Let's go ahead and look at bending in one direction, for instance. So I'm going to turn on the MY. Now this here is a representation of um, beam and column connection, right? So we have a simple beam and column connection. So you can see that where we have the beam connecting the column here, we have this sort of fixed support over here, right? So it's a rigid kind of connection, right? I can see that we have some small, very negligible moments also on the columns as well in that direction. But this is just checking the moments in one plane. Let's say if I wanted to check the moments in another plane, for instance, then go ahead. You can see here that this is now what we call torsion, right? Torsion, meaning that that beam here or the structure is bending in another plane. Can you see this? As opposed to the other side. You can see also massive deflection or massive bending on the columns, just like what I wanted to show you before, but we didn't have the opportunity. All right, so you can see here that it is bending in this direction just because of how it was loaded. Okay. All right, good. So you can see here that when it is bending in a different plane, this is where we talk about torsion, right? Torsion. So that means it is twisting. So in a way, you can see the column is twisting in this direction. Can you see this? Something like this, just because of the loading. And just to show you visibly again, I'm going to go ahead and turn on the loads so you can see this. All right, good. So you can see here that this load here is what in this direction is what causes this bending in this direction, and this one coming in the opposite direction on this span here is what causes this one over here. Likewise as well, this load here on this column is what is causing this, although this isn't torsion, but a combination of all of this on this column can what we call can actually cause what we call torsional buckling on a column, right? And we'll talk more on that when we get into the design aspect. So a combination of all these loadings is vital. Now, don't be overwhelmed by how all of this works. At the end of the day, how you experience it, depending on the projects that you're working on, will give you a better understanding of the decisions that you need to make. Okay, so don't be overwhelmed. It's by experience and by modeling all sorts of crazy structures that you'll be able to actually get a hang of it. Okay, all right, good. So let's turn this off here. Apply. And let's go over here and look at another structure. Okay, so let's come back here. Okay, good. Just want to go ahead and turn off the loads over here. Let's make it simpler to view. Alright, good. So now we've looked at here members subject to torsion based on how it is loaded. We are going to now talk about slabs, right? We talked about beams when we started off here. We looked at how the different member sizes and materials affect the beam's analysis. We've also done the same thing as well by looking at the support conditions, whether it is simply supported, whether it is cantilevered, okay? And there are also going to be different cases depending on how you are modeling your structure. We've also looked at how the analysis is affected by continuous beams, and then we looked at columns as well, almost the same thing as well, with different materials, different sections, as well as columns subject to bending forces in one direction and in two directions. And then we've looked at torsion depending on how it is loaded. Now we're going to continue here with slabs, but before we do that, I probably think it would be best let's take a 5 or let's take a 5 minutes break, and then we reconvene at 7, or rather, yeah, that's 7 a.m. my time over here. I believe that should be 9 a.m. at your time over there. All right, so we'll convene at 9 a.m. at the dots. So please, I'll be addressing. If you have questions in the chat box, let me know. I'll be addressing them now. All right.